You should be on the metallic and network solids page in your notes packet. We have 2 more pages in this packet to do. This is the one we're going to do today, and this will probably be all we get through today. We have 2 other kinds of bonds to talk about today, and we're putting them together because they're not major types of bonds. We've already talked about ionic, we've already talked about covalent. There are 2 other types, metallic and network solids, that don't make up quite as many compounds as the first 2, but they are out there, so we're going to touch on them and talk about what makes them different than the others. The last thing we're probably going to end up doing next week is filling in the bonding chart that compares all 4 types of bonding so that you can see what are differences and what are similarities kind of all in one spot. We'll see if we get that far today, but I wouldn't be surprised if we don't. So metallic bonds and network solids. Metallic bonds, as you might expect, are the bonds that you find inside metals or inside alloys. Do you know what an alloy is? An alloy is a mixture of metals. So if you could melt down a whole bunch of metals and kind of stir them together and then re-harden them, that would be an alloy. Things like steel and brass and bronze are alloys because they're mixtures of metals. The bonds that hold those atoms together are not ionic, they're not covalent, it's a specific kind, and they're called, of course, metallic. The way that these work is you have a whole bunch of metal cations, and we should know that those are positive ions, which makes sense because metals usually are positive. And all of these metal cations are arranged in a pattern, and it's called a crystal lattice. So like a geometric pattern, an orderly pattern. And within that crystal lattice of cations, you have a sea of electrons. When we've talked about ionic bonds, and when we talked about covalent bonds, the electrons have almost like a specific location. They're either shared in the middle, or they're unshared around the outside, or they're lost from one and gained by another. It's almost like they have an assigned spot, a specific location. In a metallic bond, the electrons don't have that assigned spot. They're free to move. So you can draw this picture, sketch just a little bit of it if you want in your notes. What we have here is the crystal lattice. So all of the circles with the plus signs, those are the cations. They're arranged in a pattern. And then these little dots here with the negative signs, those are supposed to be the electrons. And the lines are supposed to represent that those electrons can move pretty much in and out of this crystal lattice wherever they would like to go. The cations are fixed in place. The electrons are free to move. This gives metals some of their distinctive properties that we already learned. We know that metals are malleable and ductile. Malleable means they can be flattened into a thin sheet, like aluminum foil. Ductile means they can be stretched into a thin wire, like copper wires in your house. They have those properties because of the way the bonds work. We're going to make a quick comparison here between metallic bonds and ionic bonds. If you have a metal, again, here's kind of the same picture. We have cations, the pluses that are in a pattern. The electrons are the minuses, and they are free to move throughout the pattern. If you were to apply a stress to this metal, in other words, if you were to hit it with a hammer, those electrons almost provide the grease between the layers of cations. You want to imagine it that way. and they allow those layers of cations to slide past each other, and yet still remain bonded together. This is what makes metals malleable and ductile. Because the electrons are almost like they're providing the grease, those layers can slide, they can be molded, they can be shaped, flattened, and stretched. If you take ionic solids, on the other hand, and apply a stress, like hitting it with a hammer, the layers of the atoms would still slide, but what happens is that you end up with a repulsion between like charges. And I've got a simple little picture here to show you what that means. You may want to try to jot this down, or at least jot down part of it in your notes. When that repulsion occurs, it causes the solid to break.
Bless you.
The example that I have is a salt crystal. Table salt, NaCl. The green atoms in this picture are negative, so those would be the chlorines. The gray ones are positive, those would be the sodiums. And right now, the way that this is set up, it's kind of alternating. Every negative has a positive. Every negative has a positive. And even between the layers, it's lined up positive, negative, positive, negative, positive, negative. Opposite charges do what? Attract. That's why this is bonded and it stays together. If you can imagine a really big salt crystal, almost like a salt block like you put out for animals in the winter, and you take a hammer to it, more than likely you're at least going to break off some of it. If you hit it hard enough, you might even make it shatter. Because if you were to hit these layers with a hammer and push one layer over or two layers over, what happens to the way those charges line up? One layer would slide, and then instead of positive, negative, you end up with two like charges across from each other. You end up with negative, negative, positive, positive, and so on. What do like charges do? Repel, and so your solid breaks. So the fact that metals have electrons that are free to move is what allows them to be malleable and ductile. They can be flattened and they can be stretched because those electrons almost provide the grease between the layers of cations. That same idea that the electrons are free to move also provides metals with the property of conductivity, meaning they can conduct electricity and heat very well. Being able to conduct electricity depends on having mobile charges. In other words, electrons that can move. Because metals have mobile electrons, when they're solids or liquids, they can conduct electricity. Okay, last type of bonds are called network solids. Network solids are also sometimes called macromolecules. Do you know what the prefix macro means? Like macroeconomics? Large, yeah. If you think about the opposite, what does micro mean? Really small. So then macro has to be really large. So they're sometimes called macromolecules because actually that's what they are. If you're looking at a network solid, you're looking at a giant molecule, which is kind of cool. Network solids are molecular crystals that are covalently bonded. So the bonds that are inside this crystal are covalent. They're the kind that we've talked about already. Electrons are shared. What makes them slightly different is that you can actually see that molecule because the crystal is so large, there's so many covalent bonds, that when you look at a network solid, you're looking at a molecule. That's not something that we get to do every day, so that's kind of interesting. Because there's crystals, they have a repeating pattern of atoms, usually a geometric kind of pattern like a cube, or some of them look kind of like a rhombus, like a squished box, or a triangle. And also because they are crystals, they break along what we call cleavage planes. Did you guys do minerals last year in Earth Science?
We drew pictures.
You drew pictures.
All kinds of pictures. But like cosmetic.
When you talk about minerals in Earth Science, you usually talk about a property called cleavage. And that refers to the way the mineral breaks. This is what allows gemstones to be cut in very specific patterns because the bonds in those crystals have weak spots. And if you take a hammer and a chisel and you hit it just along the weak spot, it will actually fall apart into two relatively flat, clean surfaces. And that's pretty cool. This is how diamonds are cut. This is how other gemstones are cut for jewelry. And that's because of the weak spots in the bonds. Network solids are the same way. They have a weak spot. So if you can take a hammer and chisel and hit that weak spot, it will break along a flat, clean, shiny surface. Which leads us to our two examples. The first one is diamond. Diamond is made of all carbon atoms. So diamonds are elements. They're also molecules. You don't have to draw this picture. I just put it up here so you could see what the structure of diamonds look like. Every one of those red atoms in there is supposed to be a carbon. All carbons make 4 bonds. So you bond to 4 other carbons in a particular structure and you get a diamond. The other network solid that I have for you as an example is sand, which is silicon dioxide. And this one's a little bit more of a triangle or a pyramid. There's oxygen and then there's silicon, 2 oxygens to every silicon. So when you're looking at a grain of sand, you're looking at a molecule. And when you look at a diamond, you're looking at a molecule. That's kind of cool.